This figure that we're going to be reviewing is 20-13 that comes out of Stallcup's Electrical Design Book, Volume 2. Now, we're going to basically get into grounding auto transformers that are used basically with ungrounded systems in most cases. Now, in the book, I would just like to go with the title heads with you in case you want to read in more detail what we're going to discuss here. In our book, Stallcup's Electrical Design Book, Volume 2, page 20-10, we start with the topic head, Grounding Auto Transformers, 450.5, and we just give a good introduction there. Then we start breaking it down. A 3-wire circuit to a 3-phase 4-wire circuit, 450.5A would deal with that. Connections, making our connections, 450.5A1. Overcurrent protection, explaining the overcurrent protections and the benefit of where you place the overcurrent protection, 450.5A is an apple 2. Sensing fault currents with a transformer, 450.5A is an apple 3. Then the rating, dealing with your neutral and so forth, 450.5A4. And then, of course, we would get into detecting grounds on a 3-phase, 3-wire system. And we'd look at 450.5B. And then, of course, 3 bullets are listed there that's important. Proper rating, overcurrent protection sized adequately to sense any kind of a fault current, and then ground reference for making sure that you got everything grounded properly. And then, of course, ratings that you'd want to deal with in relationship to the auto transformer. And a continuous current neutral rating would be 450.5B1. And then, of course, the overcurrent protection overall, where you place it, would be in 450.5, B as in boy, 2. Now, we're picking up in this illustration the overcurrent protection device that would open simultaneously with a common trip, all ungrounded phase conductors, and this overcurrent device should not be sized at more than 125% of the rated phase current of the transformer. Now, it's true you won't be getting into these kind of installations. With that, you're dealing with large industrial plants, large facilities of some sort. But now, kind of reviewing our illustration, 20-13. Then we have the transformer listed there and shown as ungrounded 3-phase, 3-wire. And it's routed over to the service overcurrent protection device that would be located in the enclosure as you see in the illustration. And then you'd have your bus going up, and we would have the service equipment and have an overcurrent device for the feeder routed out to the load. And then notice the zigzag auto transformers connected into the supply side of that overcurrent protective device for the service connected in as shown. Then we're grounded, as you see, to a proper earth ground that we would select from 250.50 and 250.52 of the code, install by 250.53 of the code. But notice our zigzag transformer is 100 amp and it's rated for continuous per phase. So in the boxed in information, we're finding the amount of current that would be needed to trip open the service overcurrent protection device that you see in the left-hand bottom side of the enclosure of the service equipment. So after we do our math in step 1 in accordance with 450.5A2, 125% of 100 would be 125. So the overcurrent device would be sized at 125 amps or greater. Amount of current would trip it and open it up due to any kind of it's sensing a ground fault condition on this ungrounded system, because you want to detect it if you pick one up, so that great damage might not occur under conditions where the transformer being run ungrounded could be a problem to you if you got one fault. You know, the way that voltage would react to you at 1.732 times the remaining voltage on each leg. So that's what this figure 20-13 is illustrating. An overcurrent protection sensing device must be designed at 125% of the continuous current per phase of the neutral rating of the transformer or the phase conductors. Now we'll look at the neutral rating and how we'd size it coming up next.